So now we'll talk about redundancy. So we often say this, anything which is redundant, which means having more than one component. So in case of system design, redundancy means having additional or duplicate components within the system so that if one of them fails, there will be another one to take over. And this is done mainly to achieve high availability. So those of you who have watched the availability video will understand when I have mentioned something called availability in parallel. When I had drawn the diagram for availability in parallel, I showed how there were multiple chains of component like this and so on. So when the components are placed like this in parallel so that any one of them fails, I will be able to route through the traffic. I will be able to route the traffic through another component. So if one of them is failing, there is another one. Why is this happening? Why is another one taking? Because we have set up another system in place, another duplicate system or n number of duplicate systems in place who are capable of taking the control when the actual server dies or when the actual system or any component is failing. So this is done so that availability is kept constant. There is no change in the availability. The goal of the redundancy is to ensure that system can continue to function even when there is a single, like as I said in the availability video also, whenever availability is taking a hit, which means there is some single point of failure. So that the single point of failure doesn't happen, we want to make our system resilient enough. So that we want to make the system resilient enough, that is why we need to have redundant components, more than one components, which is going to take over whenever there is a failure or a disruption. Examples: having several servers running the same application. One server fails, another one can take the load. Now there are different types of redundancy. It doesn't really matter. It doesn't really depend on only having multiple servers. We can have three categories: hardware redundancy, network, data. Because any one of them can actually take a hit. We do not know. Maybe some hardware failure occurred. Maybe while the traffic was going, some issue in the network occurred. And data is, of course, always. Data can get corrupt. Anything can happen. So we have majorly three types. When we talk of hardware redundancy, we say that we will use multiple physical components to prevent the failure. When we have network redundancy, we have multiple network paths or multiple network devices so that the connectivity is always constant. And in case of data redundancy, we know that we use data replication techniques also. That is also something which we'll cover in case of replication. But having copies of data in multiple locations. That is the primary intention of AWS also having availability zones, right? They have multiple copies of data also in different availability zones so that if one of the zone dies out, the another one can keep serving the data. And on this note, I also want to talk about the very thin line between having a backup system and a redundancy. Redundancy is like it will automatically take the control if the system dies. But backup is more like you have taken a backup, a copy of that and stored it elsewhere in some different geographic location. When the failure happens, then it is a reactive response that you have to restore the backup and then make the system restart, and it is going to take a lot of time. The recovery is going to take a lot of time if you have backup. But redundancy means it is going to be instantaneous. Just now the failure has occurred and then another server is going to take over. Okay. So this is the thin line between redundancy and backup systems. Now let's talk a little bit about the hardware redundancy. What are the things you should be knowing? So hardware redundancy involves duplicating the critical components to ensure system can operate, all of that. Okay. These two terms are very important. Active passive, we call it active failover or active passive failover. So when we talk of active passive failover, what happens in that case is there is one, I'll just draw this diagram. There's one component, there's another component. This component was on standby. Like this was not serving any traffic. This was just there as standby. This is the one which was actually serving the traffic. So there's the active component. It will handle all the load and this one will remain idle. So that whenever there's a failure, the standby is going to take over. And this is what we mean by active and passive. There's an active and there's a passive. Standby system is kept in sync with the primary system. Like time to time, the replication of the data and everything happens, but this is not actively serving the traffic. Just the opposite in case of active failover. Here, all the components that you have, there is no system, there is no server which is sitting idle, so to say. They are handling the load simultaneously by using load balancing. Now, this is giving you performance benefits also, and it is also giving you the failover capacity, because if something fails, it will be able to take over. And because there are a lot of different servers, you have distributed the load and thus the performance is also enhanced. Multiple systems are active at the same time, and each system is handling a portion of the workload, which is why the performance is improving. And on the other hand, if one system fails, the remaining system can continue to handle the load without any interruption. Simple. So this is the two things. It is also known as availability patterns: active failover, active passive failover. When to use which one, will come to that. Now, question comes to when to use active failover and when to use active passive failover. Like we have seen in active setup, all the nodes are handling the traffic and the task. So if all the nodes are handling, which means it should be used whenever you have a high traffic and you can predict that there is a high traffic requirement and that would require load balancing. So that is one reason when you should be using active failover. When it is a critical application having lot of traffic, there should be no downtime, like zero tolerance for downtime. So then active failover makes sense. But active passive is only, but active passive you can use when you have just the opposite of these. You have lower traffic, you have cost consideration, it is not a critical application. So the example is database servers. Usually in database servers, we have this mechanism of having active passive. When the master slave or the active node is no longer able to serve, the slave one takes over, or the replica, the other standby system takes over. So this is something which we use it in database servers. But that is because we know that there is not a high traffic requirement. Database operations are expensive. Okay. And we know nobody is going to throttle the database. We write code so that we don't want to throttle the database. We minimize the database queries and so on. So I don't want to give a lecture on that. But the thing is, when we know certain type of servers will anyway have low traffic, we can think about having active passive failover. If just the opposite, having high traffic, we have to think of active failover. Active failover. Now, so far we talked about the hardware redundancy, where we know that hardware components are anyway expensive. Okay, let's talk about software redundancy. So what does software redundancy mean? In software redundancy, we will duplicate critical software components. Same thing, why we are doing, we know that. So in this case, we can do something like we are doing a process duplication. So running multiple instances, like multiple jar or multiple Docker images running on multiple instances, that is nothing but the software redundancy, wherein your each instance will be handling a portion of the workload. If one instance fails, the other one will be doing same thing. And the same goes for replication. We'll also talk about replication at length. So replication is nothing but again the duplication, copying of data, which will be like one data will have multiple backup systems, so that if you have a failure in certain data center, there will be another copy of that data being stored elsewhere, and that you can restore it back. It is easier to implement, simpler to implement, and more cost effective to implement than hardware redundancy, right? And it can provide high level of reliability and availability. Remember, all of this we are doing with the major goal of having reliability and availability in mind. So we covered hardware redundancy, we covered software redundancy. Now we are coming to data redundancy. Like I said, the replication technique. Replication cannot only be used on data, but it is majorly done on data. Replication of the data is being done. Why? Because we want the data to be always available. We cannot tolerate this thing that our data got corrupted and we lost the data forever. We should not ever end up in such a situation, especially for mission critical applications, for mission critical businesses, your healthcare, your fintech, your aviation, your banking, all of that. So we always have to ensure critical data should always be replicated. So we covered hardware, software, data, and we have finally the network redundancy. Like I said, it is simple. Like you should be having redundant network path and you should be doing network load balancing. Now coming to choosing the right type of redundancy, how should you do it? The first step is to identify what are your critical components in the system, whether your database is critical, whether your network devices are critical, or maybe everything is critical. So you have to first identify what are the critical components, your servers, your storage device, network device, database, whatever. So once they have identified it, now you have to understand what is your cost consideration, your budget of your company, your business, that you have to understand. What is the nines of availability you would want? What is the performance you would need, the level of redundancy, whether hardware redundancy is what you need or it will be doable with software redundancy. So a lot of different factors actually are there, right? So depending on that, you have to understand. Depending on that, you have to take a call. And finally, you have to test and monitor. Just by doing hardware redundancy, you cannot guarantee superb, excellent performance. You have to test it, monitor it, tweak it, optimize it accordingly. So that is all about redundancy. Let's move to the next topic.
So our next R is reliability. So we have talked about availability, we have talked about redundancy. Now we have to understand reliability. Now reliability, as the name suggests, when we say something is reliable, which means we can trust that thing or person, that person is credible. So similarly, our systems can be reliable not only when they are redundant and not only when they are available. We have to understand what are the measures which we have to make in the system that will make the system actually reliable. So that is what we want to talk and discuss today. So reliability refers to the ability of the system to consistently perform the intended function. So it is like whatever you're expected to do, that you have to anyway do without failure over a specific period of time, and it will continue to operate correctly. But there is one more thing, that it should also be able it should also be resilient enough. It will also be able to bounce back if there is some failure. So this is how I like to see it. So for example, we do exception handling, right? So we do exception handling because we want our application, our code to gracefully shut down whenever there is a problem. It should not abruptly end, right? It should not crash. So that is why we do exception handling. Similarly, any system, so exception handling is just a very small part, right? So in bigger systems there can be so many different outages, failure, the chances of this are so high. Now, in that case, it is very simple. So in that case, it is so very important that your system should gracefully handle it. So there is a failure, okay. How it is handling the failure is important, and how it is handling the failure and coming back even stronger is a measure of how reliable the system is. Try to understand this. Just because your system is available, let's say there are 10 people working on the background manually to make your system available, versus your system is resilient enough to automatically do the failover, change the server whenever there is a failover, whenever there is a failure, do the failover. There is no manual person behind the scenes who is doing this. So not because your system is available, your system will be reliable. No, anybody can manually also make a system available. But if there is a failure, how it is handling the failure, how it is trying to respond to the failures and bringing the system back to normal, bringing the system back to operational, is what the resiliency or is what the reliability of a system is about. So like it is said that it should be able to perform the function 100%, should be able to tolerate the errors, prevent unauthorized access. So reliability implies availability. If a system is available, it should be reliable. But it is not just that. Building for reliability means you have to do something more, something beyond what you are expected to do. You have to take care of security, error handling, DR, and other emergency situations you have to handle. So that is what reliability is all about. Because we know that failures in distributed systems are bound to happen. What are the types of failures? Hardware errors, okay, network outage, server failure, again application errors, your bugs can happen, your user base, some spike in the traffic, some sale has happened. Now this should also resolve quickly. They are called transient errors, and these network outages are non-transient. That is not the point, but the point is failures will always happen. So why reliability is important? So these are the points. Trust, I said, right? Credibility and trust. Your users will not be able to trust your systems if your reliability is not taken care of. Your business continuity, like availability is business, your reliability is also business. If you want your business to run smoothly, you have to ensure that after a downtime it should be able to bounce back stronger. Okay, it should not be like the system is down for a week. So automatically when you have trust, you will automatically have customer satisfaction also. So high reliability leads to better customer satisfactions. Cost savings, the more and more you can avoid these downtime situations, you will be able to save the cost. Because when these failures occur, just to understand the root cause and to mend or to repair what has already happened, there's a lot of revenue and cost and financial losses involved. So automatically your costs will be saved. There are so many different projects which go on in a company where they try to identify the operational inefficiencies and how the cost optimizations can happen whenever there is a failure. Okay, whenever there are issues, errors, failures, how the cost optimization can be done. There are different things which happen across different companies also. And lastly, compliance, of course. You have this thing, right? The SLA, the service level agreement. Similarly, if your system is not reliable, going like crashing again and again, that is not only going to have a bad reputation of your company, but it will also not meet your compliance standards, right? So automatically your business has to be shut down if you do not take care of this. And of course, legal penalties inevitable. So what are the key concepts which you have to know? MTBF, mean time between failures. So why do we need to know these terms is because when we actually do monitoring and observability and cost optimization, we have to come, we will see these kind of metrics on different dashboards, right? So when we see these metrics, you have to understand what do they mean, what do they signify. That is why you have to understand. So mean time to repair, mean time to failure, failure rate. These are the things which you have to understand in terms of reliability concept. Now, boosting reliability. So, how can we actually boost the reliability? So, different things we can do for that. So, one is to set up redundancy uh, for the critical components to avoid the single point of failure. Your servers, your database, network paths, they can be redundantly. We have discussed about this in the redundancy. Testing and validation, not only your unit test, there can be performance test, stress test, all different types of testing can be done to actually see how your system performs under stress. Monitoring analytics, like I said, observability metrics, very, very important to keep a track of how your system is performing in real time and proactively address the issues. DR or the disaster recovery plan. That is what your system resilience is about, right? So if there is a disaster, how are you going to recover from that? How are you going to recover the system whenever there is some failure which is happening is what is about the DR plan is about. Then we have load balancing because we are trying to distribute the workloads across multiple servers. So in case of load balancing, that is what we are doing. So whenever there is a single point of failure, we do not want the single server to be overwhelmed. And And when we do this, automatically we are boosting the performance and the reliability because there is no dependency, no single dependency on just one server. Automated failover, we have to implement the automated failover mechanism. Like I said, there can be 10 people behind the scenes who are handling our availability of a system, switching between servers, writing scripts and command. That is also possible. Anybody can do it. But if you do not have such an infrastructure which will in the midnight when everyone is asleep how they are going to handle this disruptions. Okay, so this is what is automated failover about. So if this thing is not being done, then you will not be able to have a reliable system. Cool. So that is about that. Reliability is important. Why is it important? How do we guarantee reliability is what we have talked about. So moving on to the next topic. Now we will talk about replication. So how does it work? Before even understanding what is replication, why do we need it? Let's try to understand the problem. So let's say you're the CEO of a startup in USA, but you're trying to expand your reach globally. So when you're trying to expand your reach, remember your servers are initially in USA and the traffic has just now started to increase. So as a result of that, the the results so as a result of that, your website is taking a lot of time to load, and even after adding resources it is not getting solved. So the problem is the network latency because of the geographical distance between where your data is located and where the data needs to be served. So that is the reason which is causing the transmission delay, thus the network latency. Now to solve this latency issue, just by adding more resources will not suffice. To solve this issue, what we need to do is we need to replicate the data to locations which are closer to the which are closer to the user. We also call them this edge locations. Okay, so we can replicate the data across multiple servers and locate it closer to users' geographical locations. So we can have multiple edge locations and we can have a copy of the data in those edge locations so that when people will search from, let's say, India or from Africa or from Singapore, if the data is served from USA, it will cause latency issue. If the data is served from the location closest to their country, then it will not cause that much latency. That is also being used by streaming companies, Netflix, even YouTube, Amazon Prime. Do you see buffering? Now, why do we need to do this? So that there is no buffering delays. Whenever you are seeing buffering, the main reason behind the buffering to happen is the network latency. Okay. Now, coming to the definition. So, what exactly is replication? It is the process of copying the data and the services from one location to another. So, it is like you are having a copy across different geographical locations. Why? Because you want to ensure the data availability, reliability, consistency. Everything is being taken care of. Obviously, if you have copies of data, the buffering is lesser. The website is always going to serve the data. Your availability is being taken care of, which is also going to guarantee you the reliability that your website is reliable no matter where the user is coming from. He's going to get the data. Consistency because you have replicated the data across different locations, so it is also going to take care of the consistency. And redundancy because you have made a copy of data across different data services across different locations, like we covered on the redundancy. Replication is essential for modern. So modern distributed system, that is the entire crux of the thing. Like your distributed systems, as the word suggests, it is distributed across different locations. So if you do not do replication, it is never ever going to solve the problem of what? Of this latency issue, like we have seen just now. And when you have this latency issue, there is a chain of problems that is coming. Like the systems becomes unreliable, it becomes unavailable, buffering occurs, causes bad user experience, and so on. Okay. It also serves as a proactive strategy for scaling applications where data are copied across multiple nodes, the latency decreases. Whenever your latency is decreasing, the performance also improves. And because of the performance improvement, the users are going to not get a bad user experience. Rather, they're going to enjoy a consistent experience no matter where the location is and no matter what the system location is. Like, no matter where the system is, no matter where the users are, they'll always have a consistent experience. Do we not have a consistent experience when we use the streaming services like YouTube, Netflix, Amazon Prime, etc.? Coming to the types of replication, the first one is master slave replication. Remember, I talked about the failover strategy. So, master slave replication means there will be a master, there will be a slave. So, what do we mean there is going to be master? There will be one primary database. So, now we are talking of data replication. So, there will be one primary database. Okay, that primary database will handle the write operations, the updates, and the changes, whatever happens to this master database, the changes gets replicated to multiple slave databases like this, who will actually handle the read operations. The slave operations, sorry, the slave servers, the database servers will handle the read operations, and this is the master which is going to handle the write operations. Now, what is the advantage of doing this type of master slave replication? Firstly, the read capacity increases. These slaves will be known as read replicas. So your read is being taken care of by different servers. Your master is going to only take care of the write and the updates. So applications can read from here. It will not affect the performance. Flexible maintenance and your backups of the entire database can be performed. Like, because the data is getting replicated, there will be no impact on the master node. So your backups are impact free, and the slave nodes can be taken offline for maintenance and they can be synced back to the master also. So that part is also being taken off. There's a separation, clear separation of concern. For read heavy workloads, this also works really, really fine. As we have written, it helps in load balancing and improves the read performance. By using the master slave replication, your read performance is enhanced because you have separate read replicas. Coming to master replication. Over here, there is no master, there is no slave. Everyone is master. So all of them are handling the read and the write. Okay. Now, when do we use which one? We'll come to that. Now, when we do this, what are the advantages? We have a load distribution. We have read capacity is not just being handled by the slave. Everyone is doing read and write. And there is a failover, like improved failover, because the data is being continuously replicated across all the servers equally. The availability is high, the failover is quick, and the downtime is lower. Because there are so many different, what do you say, so many different resources which are serving the data. So even if there is some downtime, let's say one of them goes down, there will be maybe 10 more to take care of the load, to take care of the traffic. So that is why the failover is improved. Load is evenly distributed. Now let's talk about what are the types of the replication. So master slave, we understood one master node will handle the write and propagate the changes to the slave nodes. Slave nodes will handle the read operation. We have understood this. We also understood the master replication where both of them will handle the read and write. Changes are getting synchronized between the nodes. So basically, when you need load balancing, high availability, you know that there's a lot of load which is going to come in. Master application is required. But whenever you know that the load is not that much that needs to be load balanced, maybe you can go for master slave. Peer-to-peer replication. It is like everyone is equal. Okay, each node will handle the read and the write operation. Changes will again be propagated to all nodes. This is needed for distributed systems which should not at all have a single point of failure. Okay, this is where we will use peer-to-peer replication. Next is synchronous and asynchronous replication, as the name suggests. If it is synchronous, the moment you write something, it will be propagated to all the slave nodes at the same time. So all of them will be equally consistent at any given point in time, which will give you latency, of course, but it will have high data integrity. Where do we need this? In banking applications, in your fintech, right? When you're doing cash withdrawals, let's say from ATM, you need the data. I mean, the data, the backend data, your account balance to be consistent. Asynchronous meaning it will be propagated to replica nodes after it has confirmed, the master has confirmed the write, which means there is going to be a significant amount of gap between when you have done the data, when you have actually made the changes to the data, and when it actually got updated across all the nodes. When do we need this? When do we need, like, asynchronous by nature? We know that it is not going to block the main thread. That is what asynchronous thing means. So you may need to do this when the temporary inconsistency between the nodes is still okay, it is still acceptable, then you would want to do asynchronous replication, that after some time you will replicate the data. This is also going to result into eventual consistency. Like, you may see the data is getting consistent, not immediately consistent, but it is going to get consistent maybe after 4 or 6 hours. Okay. So try to understand why are we doing these types is whenever you will come across any of these terms, you should be very clear about what is actually happening. Next is log based replication. So whatever changes you have done, we will record it somewhere similar to asynchronous. And after we have recorded, then we will use that to replicate. So this method ensures that all the changes are captured and can be replayed. So you kept a track of the changes that you are you kept a track of all the changes you have done. You are logging it somewhere. Next is trigger-based replication. So database triggers are used to capture changes and replicate them. So whenever there is a change, let's say some event occurred, and based on that, you are replicating them to the another nodes. So this can be customized to replicate only specific changes. Suppose you made an insert in the table, you made an update to some customer information. On the basis of that, I'm going to trigger the replication process. That is also possible. Snapshot replication. So at any given point in time, you take snapshots of, let's say, your database tables, right? So the entire database or selected tables, they can be periodically copied to other replica nodes. Simple to implement, but not very real time. It is not even near real time. So this is like you take a snapshot. Okay, today 6 p.m. I took a snapshot. Maybe again at 10 p.m. I'm going to take a snapshot. At 6 p.m. I had 10 million rows. At 11 p.m. I have got 11 million rows. So something like that. So at point to point, you are trying to capture, and then you're trying to replicate the data, so that not all the time you're replicating. So these are the types. Now, when to implement a replication strategy? So we have covered all the different points over here. Like I said, the very first example, global user base. So your users are coming from different geographical locations. You want to reduce the latency. You want to do a replication. High availability, because we know that server failures are inevitable. So in that case, when you do replication, automatically your redundancy point is also getting taken care of, and it is a smooth running. So high availability, load balancing, these 2 points anyway go hand in hand. So there is high traffic requirement. You have done replication, multiple servers are trying to allow the traffic, distributing the loads across multiple servers. Your load balancing is also getting taken care of. No single server bottleneck. Disaster recovery. Now, this is what is going to make your system reliable. Why are we saying that replication ensures reliability? Your system will be reliable only when it has good DR mechanisms. The disaster recovery is on point. When it will be on point? It will be on point when you have replicated your data. I have replicated my data to Delhi, Mumbai, Chennai, Pune. So I have replicated my data across India in 4 locations. So even if my data center failure is there, I can quickly switch to another location, to another replica in another location. Fifth point, read heavy workloads. We also covered this read replicas we mentioned, right? If there are read heavy workloads, we'll do master slave replication. Our problem is solved. Compliance and data residency. For companies who have stricter regulatory compliance policies for them also, it requires the data to be stored in different in region. That is next is scalability. Again, availability, load balancing, scalability, similar points. It helps you to scale your infrastructure because you have distributed your data across different nodes. And fault tolerance, of course. When you have automatic failover capability, automatically your fault tolerance is also getting taken care of because there is no single point of failure. Because of that, the systems become reliable and they'll continue to operate even if there is some failure. So with that, we are wrapping up when to implement. So with that, we are wrapping up this topic on replication.